Continuing our review of pre-cal topics, this screencast is on functions and their graphs. First of all, we're going to talk about relations. A relation is a set of ordered pairs. Any set of ordered pairs, okay? So it can be 1, 5 and 1, 7 and 2, 3. Okay, any set of ordered pairs is a relation. Now, a function is a special case of a relation. It's a correspondence that assigns exactly one value of y to every value of x. Okay, so you cannot have the same value of y going to different values of x. The set of x values is called the domain, and the set of y values is called the range. Now, function notation is just a way of telling you what's going on with the function. Every function has a label, a name, and this function is named f because it's right there. And it tells us that it's going to be in terms of the variable x, and it's going to tell us what it's going to do to x. It says we're going to square x, we're going to triple it, and they're going to subtract twice x. That's what this function does. Okay, x, the stuff you put in, is called the independent variable, and y, the values you get out, that's called the dependent variable. So if we want to evaluate f of 2, that means replace every x in your function with a 2. So f of 2 is 3 times 2 squared minus 2 times 2, which is 12 minus 4, which is 8. So f of 2 is 8. All right, evaluate f of x plus delta x. So don't freak out. All this means is replace every x up here with x plus delta x. So here we go. 3 times x plus delta x squared, because this x is being squared, minus 2 times x plus delta x. Okay, if we simplify that, that's going to be x squared plus 2x delta x plus delta x squared minus 2x minus 2 delta x. And so I have 3x squared plus 6x delta x plus 3 delta x squared minus 2x minus 2 delta x. And I don't think there are any similar terms for us to combine, so that is f of x plus delta x. Now, I already told you that all the values of x are the domain. So what happens when some values of x will make your function undefined? Remember, we can never divide by 0. So that's called a restriction on the domain. So what we have to say is x squared minus 4 cannot equal 0. And that means x minus 2 and x plus 2 multiplied together cannot equal 0, which means x cannot equal 2 and x cannot equal negative 2. So the domain of this function g is any real number except plus or minus 2. If we put that in interval notation, it would be negative infinity to negative 2, and then negative 2 to 2, and then 2 to infinity. And I use parentheses because I can go up to but not include negative 2, and I can go up to but not include 2. Now, what's the situation when we have a function involving a square root? Well, we cannot take the square roots of negative numbers if we're only dealing with real numbers. So we have to say that x minus 3 must be greater than or equal to 0. That means that x is greater than or equal to positive 3. And so in interval notation, that would be 3 with a square bracket because it can equal 3 to infinity. In calculus, we love polynomials because their domain is always all real numbers. There are no restrictions on a domain of a polynomial, and that's great. Now, rational functions, we've already seen, you cannot let the denominator be 0. Some radical functions, if it's an even radical, like a square root or a fourth root, then the radicand must be positive. or equal to 0. Some logarithmic functions have restrictions and some trig functions have restrictions. We'll get into those later on in the year. Now, piecewise functions are functions that have two or more parts, and you split up the domain. So what this piecewise function is telling us is if we're plugging in a value of x that's greater than or equal to 1, we're going to plug it into the square root of x minus 1. But if we're plugging in a value of x that's less than 1, we're going to plug it into x minus 2. So let's do an example. So what would f of negative 2 be? Well, that's less than 1, so I'm going to plug it into the x plus 2. So that's going to be negative 2 plus 2, which is 0. All right. What is f of 5 going to be? Well, that's greater than or equal to 1, so I'm going to plug it into the square root of x minus 1 piece. And it's going to be the square root of 5 minus 1, which is the square root of 4, which is 2. So that's how piecewise functions work. Now, the graph of any function must pass the vertical line test because remember that for any value of x, you can only have one value of y. So if I draw a vertical line, notice I have two values of y, so that fails. That is not a function. Now here, if I took a vertical line and I moved it from left to right, anywhere I put it, it would only hit one value of y, so that is a function. Same here. No matter where I put a vertical line on the graph of that function, it only hits it once, so it is a function. Okay, we will get into transformations of graphs in much greater detail later on in the year, but right now, if I have the graph of a function y equals f of x, and if I subtract c from every x, that is going to shift it to the right. Everything is going to pick up and move to the right. If I add c to every value of x, it's going to move everything to the left. It will not change the shape, it'll just pick it up and move it. Okay, now what happens if I subtract c from the entire function? That's going to drop it down. And if I add c to the whole function, that will move the whole thing up. Okay, now if I change the sign of every term in the function, okay, so if it starts out positive and I make it negative, then that will reflect around the x-axis. So if I graphed that, let's say I had a function that looks like that, and if I made it negative f of x, it would go over the x-axis. Okay, now what happens if I make all the x's change sign? Then that is going to flip it around the y-axis. Okay? And then finally, what happens if I make the whole function change sign and the x's change sign inside that function? Then that will reflect it over the origin. So whatever's happening in the first quadrant will now jump down to the third. Whatever's happening in the second will jump down to the fourth. Composite functions are functions inside functions. So if I have a function f that says take x and subtract 1 from it, and I have a function g that says take the square root of x, then the composite function f of g, that's the same thing as saying f of g of x. In other words, you take the g function and you put it inside the f function. So this whole thing is going to go inside there. And that would be the square root of x minus 1. Okay, now what about g of f? Okay, that's going to say take the f function and put it inside g. Okay, so now I'm going to take this whole x minus 1 and put it inside the g function. That's going to be the square root of x minus 1. Okay, and then finally, to wrap things up, we're going to talk about even and odd functions. The function y equals f of x is even if I change the sign of x and I get the same thing I started with. Nothing changes in my equation. It's odd if I change the sign of x and the entire function changes sign. Now, you may recall from a previous screencast that if we change the sign of x and then simplify, nothing changes, then we have what's called y-axis symmetry. Okay, so even functions have y-axis symmetry. Odd functions have origin symmetry. All right, let's determine whether this function is even or odd. So I am going to see what f of negative x is. So that's going to be negative x cubed minus negative x. When I cube a negative, I get a negative out, and minus a negative is plus. Notice that this is the exact opposite of what we started with. So we can say that f of negative x is really the same thing as negative f of positive x, and therefore this function is odd.